then back.
So I have to reload this. I'm
Nice.
trying to get for a second while I do that.
And we'll just get this. Nice. I'll stop it. Good. There you go. Now stop it when it points right at you. There you go, right there. Excellent.
And then take your hand and move it in circles. It's really heavy.
Yeah, well, that was kind of cool. Go ahead. Nice.
Does it feel kind of funny?
You should try too.
You get like maple syrup or something? That's just so people don't take it out accidentally. Yeah. What's happening is that the light comes inside the magnet. They're upstairs.
Okay, give me a demo.
Alright.
The happy can.
And sad can.
Say, I gotta zoom in on there. They're a little bit. Tip that one again. Happy and sad. Oh yeah, they don't. He looks sad. All right. Let's see what happens.
Alright, ready?
The happy one has to win, right? Oh, it's a sad one.
It's caught in the rat race.
It's caught in the rat race. That's right. That's the story we're going with.
Yeah, exactly. And because this was full of corn syrup.
Yeah.
He loves that sugar.
Sugar's bad for you. It slows you down. You know, I just realized what the problem is.
That's it. But it makes you happy.
But it makes you happy. No, there might be some truth to that.
Yeah.
Uh-oh, you're experimenting.
Yes.
I got, you know, they can be kind of hard to adjust again, but have fun with it.
You can see how it goes and then stops, goes this one.
Well, when they're adjusted right, of course, all the rotational motion will go into up and down, and all the up and down goes into rotational. So that's where you want them adjusted. That one there is in some strange mode. And the Cartesian divers.
Here's the Cartesian divers.
The old classic. And the soy sauce diver. a not so old classic, but well, it's Chinese.
Yeah, it's thousands of years.
Thousands of years, right? Because we're using soy sauce. I like this one because it's blue. Nice. I like this. Perfect.
Coming out here is trying to find even more about this stuff. So, when we spun it, the water ended up moving out here, and the golf ball moved into the middle. So that dense water pushed the floating golf ball.
Just throw those on for me.
Okay.
Ring without a slit. Yeah. Oh.
We have this.
And with a slit. Much faster. Excellent. So everything going okay?
Yeah.
You guys having fun?
Yeah, it's a lot of fun.
Say go, you're gonna drop the chin. Alright? You got this part? Let it go. Watch it here, watch it here.
That's cool.
Now that
Anytime.
you wanna watch this? Ready? A little bit higher.
You know, there's a little kink in there.
Coming. My name is Spartalian and I teach physics at the University up the hill. And I thought in line with this full motion thing we would do some examples of cool motion, or at least motion that may look familiar, but what I'm hoping to do is give you fresh eyes to see all sorts of cool motion that is around you. And the first thing that I'm going to show you is this. I'll tell you what is going to happen, or what I plan to do, and I would like to ask you to make a prediction. Okay? So what I'm going to do is start these balls rolling down the two tracks. And as you see, one track has a curve in it. Let's call it the curvy track. And this track is straight. Okay. So what I'm going to do when I release the two balls, the prediction is which ball is going to reach the end first. Is it the ball on the curvy track or the ball on the straight track? And there are three arguments. The first argument says that the ball on the straight track will reach the end first. Why? Because it's straight, there is less distance, so it should reach the end first. The other argument says, well, no, the yellow ball on the curvy track will reach the end first. Why? Because when it's here, it speeds up, then it moves faster, but then yes, okay, maybe it slows down, but in the end, it will be ahead of the ball on the straight track. The third argument says both balls will reach the end at the same time. Why? Because even though this ball speeds up, then it slows down and reaches exactly the same speed, so it reaches the end at the same time as the other ball on the straight track. Three arguments. Which one do you buy? Let's see. You ready to vote? Anybody? Okay. No undecideds, please. Okay. So how many people say the straight track will reach the end first? 1, 2, 3, 4, or so. How many people say the ball on the curvy track will reach the end first? 1, 2? Just 2. So we have 2 and 5 so far. How many people say both balls will reach the end at the same time? Almost everybody. Okay, you know what? This is not a democracy. Nature is not a democracy. So the majority doesn't rule here. Let's see what nature wants. Okay, are you ready to see this? I'll show you what happens and then I'll explain to you. Watch. Okay. Two people got it right. So, you know, this is nothing unusual. You see this every day. If you travel on the interstate, you see this every day. Imagine two cars moving at the same speed on parallel lanes. They stay together, right? That's what the balls do until they reach here. Now here, this ball accelerates, moves faster. It's like pushing on your accelerator, right? You push on your accelerator, you go from 60 miles, you start traveling 65. This guy is still going 60. 65 is pulling away. 65, now it slows down back to 60, but it's ahead and stays ahead, and the balls move together until this one reaches first. So now that I am explaining to you, watch it again and see whether what I'm saying is the case. In fact, I'm going to switch the balls to show you that color doesn't matter.
Faster colors.
Okay, did you see it? Okay.
I want to point out that we have cameras in the back that's zooming in on this, so if there's anything that you have a little trouble seeing, chances are Bill has it up close on camera.
Okay, so, okay. And here we have again two curvy tracks. And this is a very special, this is actually a curiosity that I would like to show you. Let me use this as a starter. So these two tracks are identical. Exactly the same. And I'm going to start the balls at the same height, so over here. And again, I'm going to ask you the question, which balls will reach the end first? This one, that one, or at the same time? What do you think? Same time, same time. Everybody same time? Are you ready for this? No surprise there. Same distance, same track, same time. No problem. Okay, here's the twist. Oop. I'm going to start them at different paths. Different legs from the end. Which one will reach the end first? This one?
Yeah.
The higher one? This one? Or at the same time? How many people say higher one? How many people say same time? How about the 50-50? Same time. Hear the click. Okay? And it doesn't matter.
Notice we're zoomed in on the end if you're not getting a good view.
Yeah. It doesn't matter how far apart they are. They always reach the end at the same time. Because this is a very special shape that gives the trip from anywhere to the end in the shortest time possible. For that reason, the two balls reach the end at the same time, no matter where they're launched from. Okay. Okay. How many? Yeah. Before I go on the next demo, there is a commercial that I keep seeing on television, and the commercial says, begins by saying, it's simple physics. Have you seen that commercial? A body in motion tends to stay in motion. Okay? And every time I see that, I get upset, and my wife always tries to calm me down. Why? because that is only part of the story, not the whole story. And here's a counterexample. This is a body in motion. I started in motion. Does it stay in motion? No. So that's only half the truth. The full truth is that a body in motion will stay in motion unless there is a force acting on it to change its motion. That's the simple physics, okay? Having said that, let me show you something that most of you, if not all of you, have done. And this is something that you can try at home if you haven't done it. What I'm going to do is just swing this around. Let me give myself lots of room. And you say, okay, so what's new? Right? You've seen this many times. So what's happening here? Why is this thing going around? And while it's up on top, it doesn't follow me like this. Yeah. Because when it's up, it's moving, and its tendency is to retain its motion and go in a straight line. And as it tries to go in a straight line, the rope pulls it in. So it goes at a slight angle. It still tries to go in a straight line like this, but the rope pulls it in. So it goes in a circle, and the rope is under tension at all times. Now, this is true for this piece of wood that is tied to the rope. What about the middle piece? The middle piece is not tied, the middle piece is free to move. Okay. But when it's up on top of the trajectory, it tends to, again, go in a straight line, but it is the bottom piece now that keeps it in the circle, because it is kept going around in a circle by the rope. And if I have another piece, same thing. So they all move as one, as we see here. You buy that? Yeah? Okay. Well, if all that is true, and I can simulate this. Okay, so this is the equivalent of the bottom piece. So I can do this. And it stays around, goes around in a circle. But I can do better than that. I can put a second weight here. And just for kicks, why don't I pour some water? If what I said to you is true, then this should stay in place and swing around as one, and I don't get wet, right? if I don't believe what I'm saying, I will get wet, and maybe I'll get some people out of their pickles if I'm not careful. So let's see if it works. Watch this. Well, that was good. So now I'll ask you another simple question. And this you should be able to answer. Because you have experience, first-hand experience. There is nothing cryptic about this. I have two items, a book and a standard sheet of paper. Okay. And I'm going to let them go at the same time. And the question is, which of the two will hit the tabletop first? The book, the paper, or both at the same time? How many people say the book? A lot of people. How many people say the paper? One person. How many people say both at the same time? One, two. Okay, watch what nature wants. Book. Okay. Is it, the question though is it because the book is heavier than the paper? Or because of something else? Something else. And what is this something else? Yes. It's wind resistance. Yes, air resistance. So, to convince ourselves that this is the case, if wind resistance is taken away, let me put the sheet of paper on top of the book and drop them at the same time. They both drop together. Okay. If the book were to drop faster because it's heavier, they would separate. And they wouldn't fall together as one. So what we need then is, for separation to occur, is for something to move faster than gravity would accelerate it. We need an acceleration faster than gravity. And one way to do this, or the aluminum, we'll do the plant next. I will try to move my hand faster than the acceleration of gravity, and if I'm lucky, you get to see that this block of aluminum will separate from my hand before my hand hits the tabletop. Okay, watch this. Did you see it come off? Okay. Which brings me to, by the way, are there any questions? If you have any questions, please raise your hand and I'll be happy to answer them. Now here we have something that you're welcome to try at home. It's a very simple gadget. There are two planks of wood that are hinged here, and what I'm going to do is put a rod here to keep the plank at an angle, like that. Here's a ball, and the idea then is to put the ball in the cup without touching the ball. Okay? And I do that. I wouldn't be asking you if I couldn't. So watch, and then I'll explain it to you. Works all the time.
Wow.
Okay? Want to see it again? All right. I'll show it again, and then I will do the explanation. Now that you know what to look for, watch the ball. Watch the path of the ball. What's happening here? Well, what's happening is very simple. I will do this. I will hold the ball here and keep holding it in place, and then let the plank fall. And then you see what's going on. What is the ball in relation to the cup? It's right above it. The cup accelerates faster than the acceleration of gravity. The ball detaches itself. It falls at the standard rate into the cup. That's all there is to this. But it's a rather nice demonstration to impress your friends if you want to build a gadget like this. Yes?
Why does the cup go faster than the ball?
Okay. It changes its speed faster than the ball. it moves the angle is arranged and the length is arranged such that the end moves, accelerates faster than the acceleration of gravity. And that's why separation occurs. It's at a particular angle about 35 degrees or so. Okay, that works. There is a long theoretical explanation, but I won't go through that. Okay. So if you want to make something like this, this is just a can that we cut a piece of. You can use a tuna can. And be sure to put some silly putty in there to keep the ball from bouncing back out. That's what there is in there. Okay. So what's that? Okay. So here is some other cool or crazy motion. Here's a piece of aluminum, which I'm going to put in this. It's another aluminum tube. Okay. So let it fall. Goes through pretty fast, right? Let's do it a couple of times so that you get an idea of how fast it moves through. Okay? Alright. Now here's something else which I'm going to drop in. Let's see how fast it falls. Okay? Go see it again. Takes a while. So what's going on here? There's a difference between these two. They look the same, but they aren't the same. Yes? The second one is a magnet. And it sticks. If it sticks, it wouldn't fall through. Let me show you. Let me convince you. Okay? There it is. I put it on the side. You're familiar with refrigerator magnets, right? You just stick them in there in the same place with your best drawings for mom to watch. Okay, so there we go. Keeps falling. Did you do the cylinder and there's a ball inside and you try to move it? It's the same kind of effect. As the magnet falls through, it generates electric currents. And those electric currents that are generated push the magnet back. It's like friction. It's like doing this. Except that it never stops because gravity is still pulling it. Okay? So the magnet is being retarded by what is known in the business as induced currents. There are currents that make this into an electromagnet. And this electromagnet has a pole that is opposite always to the pole of this magnet, so it retards it. If I can, was that clear or was it confusing? And the same effect can be shown if we have another magnet, Dave. Now this is aluminum, okay? And instead of moving the magnet through the aluminum, we'll move. First of all, this is just, again, another piece of aluminum that I brought just to show you how fast it takes to fall. Okay, pretty fast, as expected. Here's the magnet. Now the magnet, and what's this? Much, much slower. Because of those, again, currents that are generated and retarded, much like friction. It's like falling through molasses. Okay. And in fact, as I lift it, I can feel the force pushing down. If I push down, there's a force up. If I try to pull up, there's a force down. So if we believe all this, this is the last demonstration. And you're welcome after it's over to ask questions or look at this stuff. Again, we have an aluminum ring, and what we have here, wrapped in black tape, is a coil. Just regular copper wire wrapped around many loops, and as long as there is no current running in this coil, everything is cool. But things become even cooler when we try to run a current through. What's going to happen? As I run the current, this coil here becomes like a magnet. It's an electromagnet basically, that's all it is. And because the magnetic lines change very rapidly inside the coil, inside this aluminum foil, aluminum ring, what is going to happen? Much like you saw happening there, there is going to be a counter current opposing the magnetic field generated by this coil. So basically, the bottom line is that I make a magnet out of this, and I also make a magnet out of this with their poles north and north together, or south and south, but opposite poles together. And when you have the opposite poles of the magnet together, what happens? There is a repulsive force. They tend to get pushed apart. So when I energize, all of a sudden there's going to be a force. And that force will be repulsive, which will make the ring to jump. No.
Yeah, it's easier.
Okay. Want to see it again? Here we go. And in fact, we can do this. We can levitate the ring. Okay. That's it. Thank you very much. You've been a good audience.
Glad to ring.
You're welcome. I'm glad you enjoyed it.
To make it just levitate, you just press button up.
Yeah.
Oh, it was a switch on and off.
Oh.